2024 building technologies continue to improve, allows us to make our houses better. But what really is a better house? Today's episode, we're going to learn a little bit more on how to make a house healthier, more energy efficient, and just plain better. Let's check it out. Arnold Lumber has been a partner of New England builders and homeowners for over 100 years. Our goal is to elevate projects to their highest potential through top quality product solutions and above and beyond service on all projects from start to finish. Now, we're teaming up with industry leaders and the area's best builders to give you insights on the latest material technologies, best practices, and unique projects. This is Breaking Ground. Today on Breaking Ground, we're heading out to Charlestown, Rhode Island to visit with Steve DeMetrick from DeMetrick Housewrights. DeMetrick Housewrights focuses on energy efficiency, air circulation and quality, sustainability, and all around better house. So follow us along today on this episode where we take an in-depth look at all of these aspects on how to really build a better home. Come on.
I've been building for 25 years. I've been in the trades. Started off as a finished carpenter and did a lot of cabinet work. And then over the years, I started getting fascinated with how to build a better home. A house is a system. There's a lot of parts that go together to create a home, but they all have an impact on each other. As far as like the physics of it, the chemistry of the parts that go together. Through the journey of trying to figure out how to build a better house, I started learning about the Building Performance Institute, which was like BPI. They would do like a training you could get certified in to go into an existing house and figure out how to improve it.
Got it.
Piece by piece, I was on this journey of how can I make this better? And then I discovered Passive House, which is a German system for building homes, where this one guy basically on his own said, I want to build a house that all by itself, without any mechanical systems, can use this small amount of energy in a year. Mm-hmm. And that's it. And he literally engineered to build a house to that. I learned about it and took a class at RISD. And I just, through that, learned basically it was like a real deep dive. It was like the PhD of all the physics of how this thing works with insulation and air sealing and mechanical systems and windows. And built the first certified passive house in Rhode Island in like 2015, I think it was, right in Wakefield.
So now that becomes part of the core of how you build every house you build.
Yeah, because why not?
Yeah. Huh?
Like, who doesn't want to be the best builder?
Right.
Not about maybe being the best builder, but who doesn't want to do the best job? That's what I mean to say. It's not about being the best builder. It's about how do you do the best job in your job every day. I'm at a point in my career now where I'm starting to do more education and training. Like I'm teaching at the JLC show in Providence in March, and because I have knowledge I want to share, because I really truly believe it's a better building for the occupants, not for me, but just for the occupants. Yeah. What's interesting is I started out, it was about energy efficiency, and when I look at the why of what we're doing now, like if I listed all of the things that motivate us to build a house, energy efficiency isn't even on the list anymore. Right. Like our focus now is really on long-term durability, but even higher on that list for us is health, indoor air quality and health.
So you're making the house a healthier house.
It literally is. Like we have a customer that moved into one of our homes last winter in Charlestown, Rhode Island. She had severe allergies that had developed from living in a house in Kingston, Rhode Island with like a dirt basement and stone walls, and just indoor air quality was so bad. They developed really bad allergies. And every spring, like her life would shut down. She'd be losing days of work. She was taking pills every day for her allergies. She moved into our house with the ventilation system. I'll show you downstairs. Mm-hmm. She didn't even know allergy season happened.
Wow.
Just new house. And it was the indoor air environment that we created. Think of this as a perspective. Like everyone knows you drink 8 glasses of water a day. Everybody knows that. It's a healthy thing to do. The water is highly regulated. EPA regulations, like you can't move into a house without having your well water tested. Like everyone's afraid of what's in the water.
Sure.
And you're really, like I'll drink only bottled water, like for example.
Right.
Let's think about air. So you're in your house. The average person ingests 2,000 gallons of air a day. Think about that for a second. Yeah. And the mechanism that your body extracts stuff from the air is not that different from the way it extracts stuff from water. The only difference is in your lungs instead of your stomach and your veins and stuff. Think about that air now. Now, if you live in like a code-built house that has a mold problem in the basement and the house is all closed up all the time, because you got your heating and your air conditioning running, because everybody has heating and air conditioning, especially air conditioning now. And then you leave your house, get in your car, close all the windows, turn the air conditioning on. Who changes their cabin air filter in their car?
Nobody.
And then you go to your job in this glass-walled building.
Yeah.
No ventilation system.
It's crazy.
And then you leave, because you're sitting at a desk all day, and it's like, oh, I need to work out and stay healthy. Go to the gym. No ventilation system. And then you get back in the car and go home, and you're like, why do I don't feel good? Like, how does that affect your body? So 2,000 gallons of that air in all those locations where no one's paid attention to indoor air quality.
Why don't you show us a little bit of some of these aspects of health in this house that might be a little bit different if we've ever been in a house mid-construction, so you can show us what's going on.
The number one thing we do, which used to come from energy efficiency, was air sealing. Like that was priority number one for our construction. So we're building, like by code right now in Rhode Island, it's 5 air changes per hour, which is basically with a blower door test at like a certain calibration, this house depressurized, the whole volume would leave 5 times in an hour. We're building to a really tight standard. So this house, we just tested it last week. We're at just the shell, because our air barrier is the sheathing on the outside of our building. That's the majority of it. It's also our ceiling, this Intello membrane up here.
Okay.
That's an air barrier, and it's also a smart vapor retarder. This vapor control is also part of the equation here. So that's detailed to connect through to our sheathing on the outside. And it's also detailed to connect to our windows. Well, the sheathing connects to our windows. But that air tightness, we're at like 0.3 air changes per hour, which when you look at the entire square footage of all the exterior shell of the building, it's probably about, I don't know, 5 square inches of total leakage.
Wow, and the standard is 5, and you're at 0.3.
And we're at 0.3.
Wow, that's amazing.
Yeah, so that's the first one, is you have to control the air. So now that you have it controlled, now we ventilate.
Why don't we go take a look at how we can do a better job of ventilating this house?
Yeah,
Cool.
Go downstairs.
Yeah, let's check it out.
Yeah, so Tom, so this is basically our lungs of our house. And so this is called an energy recovery ventilator. And so now we've got this house super airtight, we need to ventilate it. And so that's what this piece of equipment does. And it's basically is 2 fans in here, and it provides what's called balanced ventilation, which is different. Like traditional house will have exhaust only ventilation, which is a bath fan or a kitchen range hood exhaust. Air is just going straight out. If air moves out of the house, you got to replace it with other air. But where does that come from? Maybe it comes through the garage door,
The basement.
the basement, crawl space.
Crack in a window.
This is designed to provide balanced ventilation that's coming directly from outside, controlled and filtered. So this has 4 pipes in here. There's gonna be fresh air is gonna come through this pipe here. It's gonna go through an exchange core in here, and then go through a manifold, and then we've got these pipes, you'll see them upstairs. Go through these pipes, are going into every room. So every room either has a pipe to feed air into it, like a bedroom or a living room, or has a pipe to take air out, which would be your kitchen, your bathroom, your laundry, where you have contaminants. That air is coming through the core, getting fed into the house. At the same time, an equal amount of air is getting extracted from those rooms, kitchens, and bathrooms, getting sucked into here, going through the core, and getting exhausted out of the house. The magic happens inside the core here. Let's say, for example, it has 10,000 straws in there. Every other straw is the air coming in, going through, and then every other straw next to it is the air going out. And the wall of that straw, just through natural physics, the energy gets transferred, the temperature and the temperature and moisture. So, for example, in the winter, 70 degrees inside the house, 20 degrees outside the house. You don't want to be blowing cold air into the house. So this captures that energy difference.
So in that hexagon, the cold air is jumping to the warm air?
Yep. And the other great thing about it too, we talked about health. This is a filter right here. So that fresh air that's coming in from the outside is going through a MERV 14 filter.
So not only is it fresh, it's being filtered before it even gets to go through the system.
We have them engineered specific for every one of our houses. So depending on the bigger house, needs a bigger fan. More bathrooms mean more exhaust ports. But no matter what it is, however how big the house is, we're designing for 1 air exchange every 3 hours. So every 3 hours, the entire volume of air in this house is going to get removed and replaced. So it's warm, it's comfortable, and it's healthy. When we go upstairs, actually, I can show you. You can see the ports in the kitchen and the tubes doing that, going through.
Sounds good. good. So this is an exhaust point here.
Yeah, so this area here is going to be our kitchen. One of our main exhaust points for the ventilation system is the kitchen. So you can't see the pipes up there, but that tube right there will have a register on it. And that's going to pull continuously 36 CFM of air.
And you position it in the kitchen as one area where you might want to get some of the air out anyway.
Yeah, there's the contaminants from cooking, the odors from cooking, the moisture from cooking.
So this is one spot where it comes out, and how about where will the fresh air come in?
Fresh air coming in, so this is the kitchen exhaust. So this area here is the living area. So we do have, these are 2 tubes here coming up, and here's our fresh air port right up here. So that's gonna blow about 24 CFM continuously into this living area.
Got it.
And so that's kitchen, living, and then you come down, these are bedroom and bathroom areas. So this is
more areas where, especially if you're going to be sleeping all night.
Yeah, someone's gonna be sleeping in here. There's fresh air right here. There's a smaller space, so we only engineered it only need 1 tube. So this will have about 12 CFM, 12 to 15 CFM continuous in here. And then you come in the bathroom here. So this is a full bathroom. Got a shower, the toilet, vanity. So showering, especially, there's a lot of moisture in the room. Especially like, you take a shower, that moisture is in the air and it starts sticking to the walls and ceilings and stuff. And then you leave, and a lot of people turn the bath fan off when they leave. Well, that moisture's still in here, condensed to the wall. So this ventilation system here, this is our exhaust. So we have 2 tubes of exhaust going out, and that runs, again, 24/7. So there's 24 CFM of air. So even after you leave, that moisture, which causes mold and a lot of the problems,
is continuously being pulled out.
Being pulled out, yeah.
Fantastic.
And there is, well, you can't see it right now, but there's a switch in the wall. Oh, here it is, right here. There's gonna be a boost switch here.
What does that do?
So in a typical house, there'll be a bath fan. And sometimes that bath fan, like, it'll have a button on it where you can let it run for a little bit longer. In this case, we're always running, but this switch does, if you push the button, that has 24 CFM of exhaust. It actually boosts it up to 36 for an
if
hour.
you need to move it more.
So you get a little bit more, Yeah, and those switches are in the kitchen and all the bathrooms.
The areas where you might want to give it a little extra boost.
If you want to. Just when you're taking a shower.
Perfect. We're talking about how you make your house tight and how we seal this house up, which I assume starts down here in the basement.
Actually, it starts with the plans. So we detail all that stuff in our building plans.
Okay.
Yeah, the last thing you want to do when you're building any house, especially our houses, is to make it up the day you show up.
Right.
Yeah, so in this house, typical for us is underneath our concrete slab, we've got our crushed stone for a capillary break, and then we've got a 10 mil vapor barrier that's going to stop any ground source moisture from getting up into the building. So again, we're trying to manage that moisture in the building. And then we have 4 inches of insulation. And in this house we're using, you can see it here, this is EPS insulation. It's a type 9. So it's rated for ground contact. It's about R5 per inch.
So we're standing over that right now.
Yeah, so there's R20 under the slab.
Got it, okay.
And then that sub-slab foam comes over to the wall, and we actually put a piece on the wall before we pour the slab. Okay. So then that foam goes up this wall.
So it's continuous.
Continuous, yeah. So that's thermal. You're basically avoiding thermal bridging.
Thermal bridging means allowing heat or cold to move from one.
Yeah, through a material that, like for example, like concrete allows heat to move right through quickly.
Right.
Like steel studs, for example, it's a super highway for heat to get through. So that's going up the wall. And then we got to connect from our basement walls to the walls upstairs. And we do that with just spray foam and the rim joist.
Got it.
This foam that you see here, because these are exposed, this has to meet the fire code.
Got it.
So this is a special insulation that's got a fire rated coating on it. Okay. And you can see the spray foam by code, it's got to be covered with the intumescent paint. Part of our approach to building too is we're really focusing on sustainability. Yeah. And so we spend a lot of time thinking about analyzing the products that we're putting into our homes.
Okay.
And so, for example, in this house here, that insulation there is actually recycled.
Is it?
100% recycled. They're factory seconds, taken off of old buildings.
Awesome.
So that material otherwise would be in a dumpster.
And now we're using it
and we're actually just repurposing it down
to
here.
Again make the planet a little bit better for down the road.
And it comes down to choice. Like you could buy closed cell spray foam that has a lot of petrochemicals in it, or you could get recycled. And they have different uses, different reasons why you want to use them, but for us, that's a valid reason, and it adds value to the work we do.
Let's get on the second floor and first floor and check that out.
So that basement insulation comes right up to the bottom of our subfloor right here. And that insulation too is taped. So I talked about air barriers before, that our insulation and our air barrier are aligned. And they're both continuous. So the vapor barrier is taped, the insulation's touching it. Those both come up the wall. When they get over to here, we have to transition both the insulation and the air barrier.
Got it.
So the insulation's touching the bottom of the subfloor.
Okay.
And then this cavity here, our double stud wall,
Yep.
that's going to be filled, it's going to be dense packed with loose fill insulation.
And so why the double stud wall and that pack? What's that giving us? Just
So
additional.
the gap is giving us reduction in thermal bridging.
So another break in
another thermal
energy
bridge.
transfer.
Yep.
Okay.
The only thing bridging through, because it's impossible to do completely thermal bridge free insulation. Right. The only thing actually going through that is the 3/4 inch plywood. But it's such a small area.
But
that
now you've minimized that transfer.
It, yeah. And you can see that space between the plates means that the foam's here, and then it's continuing 3/4 inch away.
Got it.
And this will be dense packed with 12 inches of a wood fiber insulation. But then our air barrier is connected by the spray foam to our zip sheathing.
Okay.
So that zip sheathing is basically taped. And then when you get up to the ceiling, we talked earlier about the Intello as our air barrier. You can see underneath here, we tape the zip sheathing to a piece of Intello before we set the rafters.
So another transition point.
Yeah,
we don't want
transitions
to have
up
any gaps.
No.
So now you're taping that transition point off from there as we come to the Intello wrap, and then
that just continues up the ceiling.
Uh-huh.
And then in this room here, we've got this gable wall that has uninsulated attic space on the other side.
Right.
So this wall here is our air barrier. So we basically are connecting that Intello to the zip system.
So everywhere where they meet is now taped off and sealed.
Yeah, they're basically, you're taking two different materials and just joining with a piece of tape.
I've noticed even where you have a penetration of a wire going through the ceiling or any of the
Let's put a piece of tape on it.
All taped up.
Yeah, this house isn't a good example because traditionally we try to minimize the number of those holes. Okay. And I gave my electrician free rein.
So you had to go back and block them
this
up.
house is a little more cut up and complicated than we typically design for. This was designed by somebody else.
I see.
So this house is an example of where we're applying our systems to a design that wasn't designed to be intuitive to be done this way.
Got it.
Versus if you go into a house that we've designed, you wouldn't see any holes in the.
You would design it differently.
We design it so that there were service cavities, so all the
but
wires
here you're
and
at
pipes
least
could
able
go
to take
through.
some of these attributes that you've developed and apply them to another design to still make it more efficient, healthier than it would have been with a common build.
Yeah.
Great.
That's absolutely it.
Why don't we take a quick look outside too and see what's going on out there?
Yeah.
Cool.
Sounds good.
Let's talk a little bit about what we're seeing here now on the outside of the house.
The outside of the house.
Yeah.
Yeah. So our air barrier we talked about is behind this. This is a European WRB that we're using.
Okay.
The only reason we're using this is because nobody in the US is making a WRB like this that's UV stable. It's got a really high perm rating of it's like in the 40s, I think.
What perm rating again, just so everyone...
it allows moisture to pass through it.
Got it.
So for example, if there was a leak, which we're trying not to have leaks,
sure.
If there's any moisture that builds up in our sheathing, it can actually dry to the outside, which is the other reason why we always build with the ventilated claddings. So this is a rain screen, they call it.
Okay.
It's like if this was shingles, it would be like the Benjamin Object home slicker or something.
Okay.
So in this case, we're actually using AZEK board and batten. So this is not vapor permeable.
Right, so we need to allow...
So we need to allow air to flow behind it. So not if water gets back there, when water gets back there,
right.
it can actually, there's air movement that will promote drying. So especially like if we're in a location here, the ocean's really close.
Yeah.
I think it's summertime, there's a lot of breezes. That's when your stuff's gonna start drying. Actually, most of the drying happens in March and April, but just the idea, the air movement, the sun's on the side of the building, it's heating up, the air gets warmer, it pulls moisture out of objects. Having that airflow through, because you can see this is like signboard in a way, little holes through all these so that air can come up and basically flow through and get out. Our windows are all detailed to be airtight to that sheathing. But they're also, because we want to be airtight with the windows, but we're also taping those windows to our WRB, and that's how we're keeping the water out.
Makes sense. And we want to do that from the outside because that's where it's going to get. And I imagine taping from the inside has some benefit, but we certainly want to stop it before it has a chance to get in.
That's the number one killer of buildings is moisture, and it's bulk moisture.
Yep.
Like the moisture from inside, like that is causing like condensation on walls and stuff that might cause mold. That's not what's taking buildings down.
Right, right.
It's bulk water leakage from poor flashing. And one of the interesting things too is when you start building a high performance building that is really, really airtight, and you get into double stud walls, thermal bridge free construction, one of the variables that you really have to understand is very little energy moving through that wall. So if something gets wet, what dries it out is energy. So if you reduce the amount of energy flowing through the wall, I think of like a 1900s house, no insulation, water's pouring in, and you're remodeling the house and you can see all this water staining, but no rot. Because there's so much energy going through the wall every season that just dries it right out. You do this, significantly reduced energy flow, significantly reduced drying capacity. Knowing that, your flashing and your water management details need to be spot on. Like for example, like overhangs, a lot of builders get rid of overhangs because it's more expensive. The amount of life the overhang will add to a building more than justifies the cost of the overhang. Most of the days when it's raining and the wind's not blowing, the siding doesn't even get a drop of water on it.
Because it's so protected.
Because it's so protected by the overhang. Yeah, it's an umbrella. It's exactly what it is.
Well, listen, we really appreciate you taking the time and showing us around and what you're up to. You're doing some great work.
Thank you.
And I expect we'll be back as the project continues to get a little bit more and see how things are progressing. So if you don't mind, we'll come back and see some more.
Anytime.
So that's it for another episode of Breaking Ground. Big thank you to our friend Steve DeMetrick from DeMetrick Housewrights. If you enjoyed this episode and want to follow along, there'll be plenty more to learn about this project. Please make sure you subscribe, like our episode, and share it with your friends. Until next time, thanks for watching, and we'll see you on the next episode of Breaking Ground.